Today in our busy world, one of the key prerequisites for many people in personal and business life is speed. This is especially true when it comes to aviation. Although air travel is almost always the fastest means of travel, many would like it to become even faster. Though the technology exists for aircraft to fly at speeds faster than the speed of sound, today's aircraft don't because of the problem with sonic booms. To help lessen the impact of these booms, NASA researchers are attempting to find a way to help aircraft move faster without causing disruptions on the ground. Our own Johnny Alonso spoke with researcher Dr. Kevin Shepard at NASA Langley Research Center to learn what a sonic boom is and find out how it works.
In the early days of flight, having an aircraft that could fly even as fast as 30 miles per hour seemed revolutionary. But a goal that pushed virtually every aircraft designer, engineer, and pilot at that time was to find a way to increase the speeds of their aircraft. As new designs began to emerge, aircraft were continually getting stronger, safer, and above all, faster. By the mid-1940s, aircraft technology had advanced to the point that breaking the sound barrier was finally in sight. After numerous attempts and failures, the world's first sonic boom was heard on October 14, 1947, when Chuck Yeager flew the X-1 aircraft into history over the desert near Edwards, California. From that point on, military and civilian test pilots were regularly breaking the sound barrier in fighter aircraft and in specialized test vehicles like the X-15. But it wasn't until 1976 that civilian passengers finally got their chance to fly supersonically, with the introduction of the famed Concorde. The Concorde had the ability to fly at over 11 miles high, 1,350 miles per hour, and travel from Paris to New York in only 3.5 hours. Unfortunately, one of the major drawbacks from the Concorde's incredible speed was the amount of noise it produced. Not only was it noisy when taking off and landing, but once it reached supersonic speeds, it created a very loud sonic boom. Sonic booms are so disconcerting to most people on the ground that commercial aircraft have only been given the clearance to break the sound barrier over water. So, are we just relegated to flying below the speed of sound? Well, maybe not. To help us understand what causes a sonic boom, and if there's anything we can do to lessen its impact, I spoke with Dr. Kevin Shepard at NASA Langley Research Center to find out how it works.
Any vehicle traveling faster than the speed of sound creates a sonic boom. What actually happens is shock waves, which are pressure rises, are developed near the airplane, and as those travel to the ground, what we perceive as a noise, in fact, is this sudden pressure jump, much like a rifle crack or a balloon popping. In fact, what you hear are two booms, closely separated in time, boom, boom, and you could visualize it as two rifle cracks or as two claps of thunder,
Sure.
Closely spaced in time.
What is the speed of sound? And well, how do you measure the speed of sound?
We like to say Mach 1
Okay.
is supersonic, everyone knows that expression. Mach 2 is twice the speed of sound, Mach 3, 3 times, and so forth. The actual speed depends on the atmospheric conditions. So if you're near the surface where it's typically quite warm, speed of sound is 700, 750 miles an hour. When you're at altitude where airplanes fly, it's a little lower, maybe 600 miles an hour. So, for example, Concorde traveled at Mach 2, 1,200 miles an hour is roughly the speed it traveled at.
A common misconception about the sound barrier is once it has been broken, there is just one quick noise, and then the noise dissipates. One reason this misconception is so prevalent is that most people hear a sonic boom when they're standing in a stationary position on the ground. What actually happens is when the aircraft breaks the sound barrier, it continues to break it as long as it's flying supersonically.
Any observer on the ground, hears the airplane go by. If you picture a boat in the middle of a creek and the bow wave from the boat, you watch the boat go by, and a little while later, that bow wave passes you on the riverbank. People further down the riverbank have the exact same experience. So what's happening is, in the case of the airplane, it's dragging this boom carpet behind it all the way across the country.
Depending on weather and altitude, the sonic boom created by the aircraft can be heard in a path of about 60 miles wide for the entire distance of the flight. So, if an aircraft is flying from New York to Los Angeles, the sonic boom will be heard consistently across the country in a 60-mile wide path. This is the foremost reason supersonic flights are not allowed to fly over land in the United States.
Yeah, most people find the sonic boom unacceptable. These are two loud sounds. They're startling, they're annoying, they tend to shake buildings, rattle windows, and so based on experience with Concorde, for example, it just doesn't happen. There is no commercial overland supersonic flight.
But revolutionary steps now being taken by NASA may change that in the future. So, Dr. Shepard, are we stuck with the fact that we'll never be able to fly over land at supersonic speed?
We're hopeful that's not the case. The current programs we're working on are aimed at allowing supersonic overland flight. The hope we have is based on a recent flight test which demonstrated that we can in fact shape the airplane in such a way that we can shape the sonic boom and it sound different, sound more acceptable. This has been known in theory for 40 plus years, but it was only demonstrated within the last couple of years with a real flight vehicle. Now that's part of the story. The real issue is, can we get the boom low enough for people to find it acceptable? We think we can reduce it. Can we reduce it enough? We're hopeful, and we're hoping we'll have a flight demonstrator within the next few years.
So, Dr. Shepard, how do you test sonic booms? I mean, is it always in flight, or can you also test it on land?
We'd love to do it in flight.
Okay.
But building vehicles, as you can imagine, is very expensive, and you don't get to do it very often. So if you've got a theory that this kind of vehicle will make a different kind of boom than this, yeah, we'd like to build the vehicles, but that's not going to happen. So in terms of figuring out what people might find acceptable, we simulate the sonic booms using ground-based simulators, which are basically loudspeaker systems, where we can produce the sounds that would be developed by certain vehicle types. Sure. And that's the simulators that we have here at Langley. They're being used for that, because we hope that will guide the design of the airplanes to ultimately lead to an acceptable sonic boom.
Can you give me some examples of what you test in these simulators?
These simulators are basically loudspeaker-based systems, so we can make sounds, and we can design them to make sounds that sound very much like real sonic booms. We bring in human test subjects, members of the public, and in essence they give us their opinion. You know, this sonic boom versus another, which actually corresponds to one airplane versus another, because we're trying to design airplanes to give us the right sonic boom. And so the characteristics of the boom is what they're assessing with their ears. If we can solve the sonic boom problem, then we can have supersonic flight over land. People and goods can get from place to place quicker, because our overall aim here is to make the air transportation system more efficient, safer, in this case faster, but also environmentally acceptable. That way we save time, we save money, we have a more efficient system.
That's it for this edition of NASA's Destination Tomorrow. I'm Kara O'Brien. For all of us here at NASA, we'll see you next time.